Okay, so today we're going to continue on with integration and something called the fundamental theorem of calculus. Here's a helpful hint. If it's called the fundamental theorem of calculus, it's probably pretty important, but not as important as someone's field trip form that she neglected to ask me to stand while she was in class 5 minutes ago for 48 minutes. I forgot.
You're the last one, see?
Whatever. We'll blame traffic.
Thank
See you
you.
later. Okay, so you did half of this on Tuesday. Should be easy peasy. Okay, we're going to talk about the fundamental theorem of calculus. We're going to talk about the mean value theorem. Wait, we already did the mean value theorem. Yes, we did, but there's another one. This one's for integral. By the way, what's the mean value theorem for derivatives? Bingo. Slope from calculus equals slope from algebra. We're going to talk about the average value theorem tomorrow, or the next day, some other day, okay, which is also known as the meltdown theorem. And then we're going to start today with the second fundamental theorem of calculus, which you did on Tuesday and didn't even know it. And then one of your goals for today, if you haven't already done so, is please try to meet somebody new. Okay. Somebody sitting at your table is not somebody new. All right, so here we go. We did this on Tuesday. On the surface, this seems fairly easy. I'm taking the derivative of an integral. The analogy I would have for you is if you take the square root of a squared function. Don't they just undo each other? And the answer is yes. But there's some subtlety here that we need to be aware of. Notice that the lower limit of integration is a, and a is some constant. Whatever number you want it to be, the number is irrelevant, but it has to be a number. The thing up on top is some function, and we're going to start with something simple like x. The one thing that you should notice is that we're starting with f of t, but we're ending with f of x. Now, why does that happen? Sometimes it helps if you see what this looks like with an example. So let's take something simple like x squared. And we'll go from 0 to x of t squared dt. So we'll actually use a function, not just some made-up function f of t. What's the antiderivative of t squared? No. Yeah. 1/3 t cubed. Okay, so I'm going to end up taking the derivative eventually, but I'll just put that out in front. 1/3 t cubed. This following notation you don't need to understand. You just got to go with it because we'll get there in a second. So I took the antiderivative, and then what I'm going to do is I'm going to plug in x and I'm going to plug in 0. Okay. Oh, you know what? Hold on. Let's change it. Let's make it more interesting. Instead of 0, let's make it 2. Okay. This will make it a little saucier. Okay. Plug in x. I get 1/3 x cubed, and then I have to subtract. You'll see why later. What happens when I plug in 2, and when I plug in 2, I get 8/3. Now, how that happened is not important. The one thing I forgot is then we're going to take this puppy and we're going to take the derivative of it. What's the derivative of 1/3 x cubed? X squared. What's the derivative of 8/3?
0.
0 disappears. And so you'll notice we started with t squared, ended up with x squared. Now, to make your life a little bit easier, you may want to consider the other thing. What you actually need to do, if this is not just plain old x, is you need to include the chain of that function. Well, what's the derivative of x? 1. Okay, so you chain on a 1 there. It doesn't affect the outcome at all, but in my next example, you'll see that it does. So the derivative of an integral replaces the t's with whatever function is up on top, and you're done. Notice there's no plus c, because it's a definite integral. Pregunta, sir.
So you do that, you do the antiderivative.
Yes, sir.
Then you do the derivative,
Correct.
plug in the bottom at the number of that, I forget, this antiderivative thingy.
Yes, sir.
Squiggly line.
Yes, sir.
Then you get x.
Yes, sir.
And then you times it by whatever at the top.
Yes, sir.
Okay.
Okay.
Awesome.
Yes, sir.
Let me show you an example again. Okay, so let's ramp it up a little bit. You don't know how to take the antiderivative of the square root of t squared plus 1. We haven't covered that yet. But you don't need to. If you understand the fundamental theorem of calculus, part 2, then you know that the derivative of an antiderivative is the same thing except you replace the t's with this function up on top. Sorry, went out of control there. Put x squared in for t. You get x squared squared, which is x to the 4th. And then you have to chain on the derivative of that. Chain, chain, chain. And you get your answer. If it's a function you can work with, like my first example, then it shouldn't be a big deal. However, if you understand the second fundamental theorem of calculus, you can save yourself a lot of hassles by understanding what's going on. And I can guarantee that on the AP test, they're going to give you a function that you don't know how to find the antiderivative of, to test to make sure that you understand the fundamental theorem of calculus. Okay? Would you like another example? Yes? Okay. Let's take the derivative of the antiderivative from 5 to x cubed of t to the 5th minus 4 over t squared dt. That is not a function that we can take the antiderivative of, because I'm sure you all recall that there is no quotient rule in antiderivatives. But again, if we understand the process here, the derivative of the antiderivative means wherever there's a t, you replace it with this x cubed. So this becomes x to the 15th minus 4 over x to the 10th. Chained on with a 3x squared. Done. Plugged in x to the 3rd wherever there's a t, simplify, and you have to remember to chain on the derivative of that function. Yo.
How do you get x to the...
Yeah, how's that?
Oh, sorry. I screwed up my own problem. Should be 6. I thought that was a 5. I do know that 3 times 2 is 6, not 10. I just misread my own problem as 5. Thank you. Good catch. Okay. We good? Problems? Outstanding. This is going to be fun. All right, put your pencils and your style eye down for a second and just be mathematical sponges and see if you can follow along with this extravaganza. So we're going backwards. We're going backwards because I think this is an easier process than going in the correct order. What I'm going to do is prove really the heart of the lesson today, and that is the fundamental theorem of calculus part 1. Part 2 doesn't happen very often. Part 2 you're going to do ad nauseum. You know what that means?
Yeah,
Ad nauseum literally translates into until you puke. So we're going to start with this. This you already know because we just did it. The derivative of an antiderivative from a to x is going to be f of t becomes f of x. Okay, good. So we start with 2 functions, capital F and capital G. They're both antiderivatives of lowercase f, except they're separated by a constant, meaning graphically one is higher or lower than the other one. That's the only difference. They're the exact same shape. So let's say they were parabolas, one is going to be shifted up c or shifted down c, but they look exactly the same. Okay? We good so far? Beautiful. Now we define g of x as that. It's one of the antiderivatives of this function f. Okay? So the big question is, what's g of a? Tom?
Is it lowercase f of a?
Nope.
Anybody else?
Maggie, is that you? Who's talking? Oh, sorry, Kaylee.
0.
Why?
Because A and A are meant, or like are the same, so it doesn't, the integral is nowhere.
Perfect. Okay. You'll recall one of the properties we had is that you would have the area under a segment which has no whoops, what did I just do? Equals 0. Okay, so continuing on. That next step is this step, just plugging in A. So G of A is equal to F of A plus C. We don't know what F of A is, but we know that G of A is equal to 0. Therefore, all of a sudden I know what C is equal to. It's equal to that puppy. Negative F of A. So regardless of what else we do, C will always be negative F of A. Then we do it again with a different letter. Let's use B this time. G of B would be equal to F of B minus C. Not 0 this time because now it's something other than A, so there's going to be area under the curve for both of them. Okay, which gets us to this. All right, F of B minus F of A. Where did this F of A come from? It came from right there because we know what C is. And therefore, that leads us to the following. That is the fundamental theorem of calculus. In fact, it's so important. Oh, you snuck up on me. It's a good thing you're not a ninja. Thank you. Are you a ninja? No. Okay, good. I guess I was.
That's the one who left the last time you did the case.
Their shoulders are sore from carrying around the attitude. I'm so upset my clicker stopped working. Oh, there we go. So it leads us to this. It's so important it gets an orange rectangle. This is as important as basic derivative stuff. This is going to allow us to find the area under the curve of any curve. Not just pretty little geometric shapes like we've engineered so far. And some of you, or actually most of you, have got this whole antiderivative thing under control. If you've got the antiderivative thing under control, then this should be easy peasy lemon squeezy. In case you didn't get it the first time. All right, so let's try one. You all know what x cubed looks like, right? Okay, and the nice thing about it is you don't need to know what x cubed looks like. If you got kicked in the head by a horse over the weekend and you forgot what x cubed looked like, it's okay, you can still do this. Take the antiderivative, plug in 3, plug in 0, subtract those two values. Okay, so I'll lead you through this one because I got to show you some notation. What's the antiderivative of x cubed? Beautiful. 1/4 x to the 4th. Now here's the notation. You use a vertical segment, you put a 0 on the bottom and a 3 on top. That means I've taken the antiderivative of x cubed already, 1/4 x to the 4th. Now I'm going to plug in 3 and I'm going to plug in 0. If I plug in 3, I get 3 times 3, 9 times 27, 81/4. And if I plug in 0, I get 0. So therefore, 81/4. Not because I don't trust my math, but because you also need some practice. Get out your calculators and confirm that with FN and T. Okay, yes? Good to go? All right. So then let's talk about two different problems. Let's change this one. Without fn inting, don't cheat, what is that equal to? Now, you could grind it out, like we did the previous problem. However, if you're sneaky about it, you can get the answer without having to do any calculations. Ideas? 0. Why? It is a function that's symmetric about the origin, meaning it's the same thing right side up as upside down. So for those of you that are good with graphing, you should be able to do it without this. But, ooh, that's kind of close. But anyways, this area here is going to match that area there, and therefore we get a value of 0. Okay. What about this one? 0 would be a good guess. Wrong though. No, not 0. You said not 0, right? I heard you wrong. I thought you said 0, but you actually said not 0. Right. There's not an easy way to do this. We're going to actually grind the answer out. However, if you want to be sneaky about it, I could do that. Ooh, that's supposed to be a 0, sorry. Does everybody see why? It's a parabola that's symmetric about the y-axis. It's an even function. It's reflexive above around the y-axis. So if I just figure out the right-hand side and double it, I'll have the area. But even if we do it the old-fashioned way, we'd have 1/3 x cubed evaluated from -3 to 3. That would be 3, 9, 27. 9 minus -9 would be 18, I think. Can somebody confirm that for me, please? FN, it didn't tell me what you get. Good. All right. Now, any one of those 3 problems could have been done by just grinding it out. You know how to take the antiderivative of x cubed and x squared. But there are tricks that can save yourselves a lot of hassle. Personally, I find it frustrating when I don't realize that there's a trick and I do all the math and then I get an answer like 0 and I realize, oh, I should have been cleverer than that. I should have recognized what my answer was going to be. But if you don't, that's okay as long as you get the correct answer. All right, make sense? How could we make it more interesting?
Bigger numbers.
Bigger numbers? Go from like 0 to a gabillion?
Sure.
All right, yeah, I'm not going to do that. It's going to be too, I don't know how to put a
More
gabillion in there.
variables.
What's that?
More variables.
More variables. How about more letters?
Love
Okay. Well, that's not too bad, right? You can do that. Go, do that one. I'll save the fun one for next.
it. It's gonna get worse.
This is easy peasy.
That's what it is.
This is when like after the D, you solve for F, right?
Say again?
Like if you had F and X in there, and I said D of F, you solve for F, right? Like you know that D of X,
Yeah, the dx.
that part is for like what variable you solve for.
100%. So you only got one variable in there, so it's just holding a place right now. That doesn't become relevant until later.
Yeah, because it's 2 variables, 1
Is it 14?
Oh, it's
I did it fast.
X to the 3 halves. 3 halves X to the 3 halves. Oh, there's 3. And that's why it's 14. There's 1 times 3. And then there's Oh, yeah.
Yeah.
Exactly. 14, yes?
Yes.
Beautiful. So I started by rewriting my function as 3 times the integral of x to the 1/2 dx, because the square root of x, same thing as 1/2. Took my antiderivative, plugged in 4, plugged in 1, and subtracted. Easy, yes? Beautiful. Okay, so let's bring some more variables in there. I shouldn't say that. Not more variables, let's bring more letters in there. Ready? Yeah. This will be fun. Go get them.
I don't like it.
Sorry?
It's scary.
I understand.
I'm afraid.
Don't be afraid. It won't hurt.
Are you kind of a
No, I'm not sure.
Oh, God. I think I dropped them. I'll tell you one sentence.
Yes, it's no, yeah, it's yeah, so I was right.
No, it's already.
One minus 0 is 1. Are you sure?
I did.
Okay, got it? Yes? Michelle, what is it? 1. Beautiful. Okay, so this leads me to an opportunity for me to go off on a tangent. In case you didn't know, coming up we have this pesky little thing called the final exam. And with that final exam looming, I thought I would talk a little bit about some things that you can do to help yourself. So for instance, some of you did not know the antiderivative of the secant of x because you haven't burned it into your brain yet. And as much as I rave about not being memorizers, at some point you just have to know things. So for instance, if I ask Armin, what's the derivative of sine?
Cosine.
Bingo. You didn't have to think about that, did you? What's the derivative of x squared?
2x.
2x. Okay, so there's certain things at this stage that you already have as part of yourself. You know how to do those kind of things without having to think about it. The antiderivative of secant squared caused a little bit of problems for some people. Yes?
Yeah.
So a lot of note flipping, and that's fine because you haven't really practiced it enough to make it part of your repertoire, if you will, of calculus knowledge. In order to help you get to that point, you've got to come up with some technique that's going to help you individually. And some people are flashcard people. You may have already started making flashcards of important stuff that have come up in the class. Some of you are cheat sheet people. You make a cheat sheet for the entire semester as if you were going to cheat on the final exam. It takes everything out of your notes and condenses it into one nice little format. Whatever's going to help you prepare for the final exam and prepare for the AP test over in May, you got to get going on it soon. Okay, for the final exam, you basically got 2 weeks for it. And if that means finding an app that does flashcards, if it means getting some 3x5 note cards and starting to write things down on that so you can practice it, you got to do something. Okay? Questions? Why do you seem confused about the cheat sheet? You can use a cheat sheet on the final, that's okay.
Wait, really?
Yeah, you'll just get a 0.
I thought I had
So, for instance, most of you probably know the derivative of sine and cosine, maybe even tangent. You might not remember the derivatives of cosecant, secant, and cotangent. These are things that you need to know. And you're only going to know them by practice. Okay? Or just pure memorization. So for those of you that are memorizers, get some flashcards and get going. Question?
Is there a way you can find out the derivative of secant without actually knowing?
Yes, but it's way too time consuming. You'd have to write secant as 1 over cosine squared, do a quotient rule, and then simplify it. It is doable, but probably not in the time frame that you're talking about. And again, as much as I'm not a fan of that, there is some point you just gotta buckle down and get it into your brain somehow. Okay, last one. Now you'll recall I said we've never really done the derivative of an absolute value. We're also never really going to do the antiderivative of an absolute value, but you can find a value for this. Now, when we look at examples like this, I'm going to talk while you're thinking. When we look at examples like this, and you're working on the homework tonight, you're going to hear a calling. And that calling is going to be your calculator. And your calculator is going to say evil things like, just FN into me. Just plug it into me. I'll give you an answer. I never lie. And you know what? The calculator doesn't lie. It will give you the answers. But you're not going to know how to solve the problem. At some point, you're going to have to do the antiderivative. You will see on the next quiz, when I give you a problem like this, one of the things it's going to say is you must show an antiderivative, or it will be a non-calculator quiz or test. So you have to be able to do that antiderivative part and can't rely on the technology. On the AP test itself, if you're given a calculator, you use your calculator to do everything. On the calculator portion of the AP test, you will never do an antiderivative. You will FN int the snot out of everything. Because they're assuming that you have a calculator and know how to use it. That's not what they're testing. Me, however, I'm going to be testing whether or not you can do an antiderivative. So the question is, how am I going to find the area under the curve of that absolute value function from -2 to 3? I'll give you a couple minutes to try some different things, and then we'll come back together and talk about it.
But
That's not. That's always, it's never, I know.
yeah,
Oh, you made it.
Hey, would a picture help?
I know what it looks like.
that's not way bad. Say, oh, hi. Say, hey, you're so
That's
You see, like that, too, so I thought that's just going to be confusing.
Well, I think Mr. whatever his name is knows that like
Okay, good.
you know what is it called? I know what you
Yeah.
I was like,
So you can also find this one. Richard, you can plug -1 too. This one like
Okay, so let's talk about the picture first. Why does that picture look the way it does? Say again.
Stupider? That's a word now.
Okay, so don't get this problem confused with just a plain old absolute value. This is not a v function. That's the absolute value of x. This isn't x, it's the absolute value of some function. And as she just said, what the absolute value does is it takes anything below the x-axis and flips it up. Okay, so that's the picture we get. Now the question is, how do we find the area under the curve of this picture? If you just did it by dropping the absolute value bars, we would get a negative answer because a big chunk of that picture is underneath the x-axis. I don't want that, I want it to be positive. So Tom, what did you do?
I found the area of the curve under the section where it wasn't inverted, that's still in our range, and then I found the area of the section.
Okay, hold on 1 second. Can you all find these points? I mean, yeah, you can read them off the graph as -1 and 3, but could you find where that function crosses the x-axis? Yeah, set it equal to 0 and solve. Okay, good. So you took the region from -2 to -1 and just founded the integral or the area under the curve of that thing.
Yeah.
Okay, then what?
Then I took the region from here to here.
Okay, from -1 to 3.
Yeah, and I found the area of that as if this didn't have the absolute value on it, and then I just changed it.
Perfect. Okay. Which means you have to do this as two separate integrals, the blue part and the red part. The red part, when you do it, you have to change the sign because it's below the x-axis. As Tom said, we want it to be above the x-axis, which means you just change the sign of the answer. Okay, so we get that. This first part is the blue region. That's the area under the curve from -2 to -1. That's just a straight up, simple antiderivative. The second part, the second integral I should say, is the red area. And you'll notice that the function looks a little bit differently because I multiplied everything by -1. Now, did you have to do that? No, you could have just calculated the answer with the regular function and changed the sign of it. You could have left the -1 out in front. But I chose to multiply it out because I'm silly. And I don't have an answer. I didn't finish the problem. But some positive value because they're both above the x-axis. It doesn't matter what the function is inside the absolute value bars. You just have to find where it crosses the x-axis and create separate integrals for each of those regions. And then the last thing you have to do is decide, do I change the sign of it or do I leave it alone? Notice the blue region we left alone because it's automatically above the x-axis. The red region we had to change the sign because it would normally be below the x-axis. Make sense? Beautiful. We're done for today. Now, a note about your calculators. I already talked about how they're going to call to you to do all your homework. However, if your calculator is one of those where you have to use the FN-int notation, I can upgrade your calculator's operating system. Okay. The problem is it's a time-consuming process, and some calculators take up to like 20 minutes, so I can't do everybody's at once. And there is also a slim chance that it could break your calculator. It's only happened once in like 10 years, but I just want to let you know ahead of time. there is a chance it could like fry out your calculator. If you would, for those of you that don't know what I'm talking about, if you have the FN int and you type in the notation, look at somebody else's calculator. The other calculators with the newer operating systems are a little bit more elegant because you actually get the picture with the S thing and you just plug and chug. If you want to try to upgrade your calculator, I can do that for you. The easiest way to do that is just come into class before class starts and ask me to upgrade the calculator. We'll just let it work while you are working. That's the Who doesn't have the new fancy one? Who has the old FN int technique? Just now? All right. If you want me to try to update it tomorrow, I can do that.
You think it's, because I've got like, my calculator has such huge pixels that I don't think that little picture would be able to appear.
It works.
Does it?
Yeah. Trust me.
Okay, I guess I'll do it.
Wait, the worst that can happen is it just breaks the calculator. Then you just steal something.
I have a plan. Oh, up there.
Pen.
Mystery.
Pen.
What day is the quiz on?
Not this week.